January 2013. A small team at Google releases a tool called word2vec, pointed at a corpus. Wait a few hours. Out comes a set of word vectors with properties nobody had quite seen before. Before word2vec, training word embeddings took weeks on a supercomputer. After word2vec, hours on a laptop. That is not an improvement, that is an earthquake. Mikolov did two things. He simplified Bengio's neural language model until it was almost trivial. Then he added a training trick called negative sampling that made it stupidly fast. The result was a paper on L5E3, some code on Google Code, and a field-wide direction change that happened in weeks. Last video I told you Bengio, 2003 invented dense word embeddings as a side effect of building a neural language model. It worked. It was slow. Nobody outside the neural net community really noticed. Today we watch what happens when a Google engineer takes that slow idea and makes it 1,000 times faster. Because sometimes speed is the difference between a curiosity and a revolution. The puzzle. Bengio's model was slow because he was solving the full next word prediction problem. Given the previous words, produce a probability over every single word in the vocabulary. 50,000 outputs, one softmax, every training step. That's the bottleneck. Mikolov's insight, you don't actually need to solve the full problem. You just need vectors that carry meaning. So shortcut the training. That's the whole game. Today's 3 beats. First, CBOW and skipgram. The two architectures Mikolov proposed. Same idea, opposite direction of prediction. Second, negative sampling. The trick that made everything 1,000 times faster. Deceptively simple. Third, why hours not weeks was the real revolution. And what actually changed versus Bengio 2003. Because it's less than you'd think. Beat 1. Two architectures. CBOW, continuous bag of words. Given the surrounding context, say 4 words on each side. Predict the middle word. If I hand you quick brown jumps over the lazy, the network's job is to guess fox. Simple, and skipgram flips it. Given the middle word fox, predict each of the surrounding context words. Same idea, opposite direction. Both architectures share the key move. A single hidden layer of small dense vectors, say 300 dimensions each. That layer I is the word embedding table. The network isn't about the embedding. The embedding is a layer. When training finishes, you throw away everything downstream and keep the lookup table. Those 300-dimensional vectors are word2vec. Practical difference between the two. CBOW is faster to train. Skipgram works better on rare words. In the paper Mikolov reports, skipgram wins on the analogy benchmarks. The king minus man plus woman task. So most people using word2vec today are using skipgram. But, spoiler, the difference between CBOW and skipgram is smaller than the difference between good and bad hyperparameters. Everyone acts like they're radically different. They're not. Beat 2. Negative sampling. The speed trick. Remember Bengio's bottleneck. The softmax over 50,000 output words. That's where all the training time went. Mikolov's move. Don't do it. Instead of asking what's the probability of every word being here, ask a much cheaper question. Given this word context pair, is it a real pair from the corpus or a fake pair I just made up? Binary classification, 1 yes or no per training example. How you make the fake pairs. You pick the real pair, say fox and brown from your corpus. Then you pick a handful of random words that didn't appear near fox, banana, stapler, quicksand. The network's job is push the fox-brown pair UP in likelihood and push the fake pairs down. 5 fake pairs per real pair is common. That's a factor of 10,000 fewer calculations per training step. That's where the 1,000 times speedup comes from. Now the important question, why does the shortcut still work? If you're not solving the full prediction problem, why do you end up with good vectors? Turns out, the binary real vs fake task pushes real word context pairs vectors together in the embedding space and pushes fake pairs vectors apart. The net effect on the vectors is essentially the same as the full task. Same geometry emerges. That's the whole magic of Mikolov's paper. Beat 3. What actually changed versus Bengio 2003. Here's the honest answer. Not the architecture, a shallow neural net with a middle layer embedding. Same idea. Not the objective, predicting nearby words from a target. Same idea. What changed was the training trick and the scale. Faster training meant Mikolov could use a way bigger corpus, 100 billion words from Google News. Bengio was training on tens of millions. The Google News corpus was the killer detail. 100 billion words is a lot of context. Enough that even really rare words get seen in enough context to learn a good vector. Enough that gender, tense, and country capital analogies actually emerge as consistent directions in the space. Bengio couldn't scale up. Mikolov could. And that difference is where the king minus man plus woman trick lives. One more piece. Mikolov released the code. On Google Code, freely downloadable. That mattered enormously. Anyone could reproduce the king minus man plus woman result on their laptop. Anyone could plug word2vec into their own NLP system. Within a year, half the papers at every major NLP conference used word2vec embeddings. This is the moment NLP became a deep learning field. 3 takeaways before the quiz. 1. CBOW predicts a word from context. Skipgram predicts context from a word. Same idea, opposite arrows. Practical difference is smaller than people claim. 2. Negative sampling. Instead of a full softmax over 50,000 words, do a binary yes or no on 1 real pair and 5 fakes. That's the 1,000 times speed up. 3. Versus Bengio 2003. The architecture barely changed. The training trick and the 100 billion word corpus did. Speed unlocked scale. Scale unlocked magic. Quiz 1. What's the difference between CBOW and skipgram? A. They use different math. B. CBOW predicts word from context. Skipgram predicts context from word. C. Skipgram is not from word2vec. Or D. CBOW is deeper. B. Opposite arrows. Both use a shallow net with a middle layer embedding. The direction of prediction is what differs. CBOW is faster. Skipgram is better on rare words and analogies. But the practical gap is smaller than the marketing suggests. Quiz 2. What does negative sampling actually do? A. Removes negative words from the corpus. B. Replaces the 50,000-way softmax with binary yes or no on 1 real pair and a few fakes. C. Trains only on antonyms. Or D. Deletes rare words. B. The speed trick. 10,000 times fewer calculations per training step. And it still produces the same vector geometry because pulling real pairs together and pushing fake pairs apart winds up in the same place as the full prediction task. Almost embarrassingly simple. Quiz 3. What actually changed versus Bengio 2003? A. Word2vec used transformers. B. Same core architecture, new training trick plus a 100 billion word corpus. C. Everything changed. Or D. Nothing changed. B. The honest answer. The architecture is basically Bengio's shallow neural language model. What changed was negative sampling for speed and the Google News corpus for scale. Speed unlocked scale. Scale unlocked the analogy magic. 10,000x more data is where the magic hides. Back to the puzzle. Mikolov shortcut Bengio's expensive training problem and scaled up the corpus. The result was fast, cheap embeddings that captured meaning, shape, structure. NLP pivoted overnight. But Stanford didn't buy it. They thought Google's predictive approach was philosophically wrong, so they built their own competing method on completely different math and got almost the exact same vectors. That's next. Next time, GLOVE, Stanford's counter theory, different math, near identical results, and a Levy Goldberg paper that reveals both methods might be the same thing in disguise. Hit subscribe.